It's like you have the left and the right hemisphere. You have the pretty part of chemistry, more descriptive chemistry. That's kind of the drawing and the Lewis structures you did yesterday. And then we have the numbers part, and we're doing numbers part. Now, before we talk about this and all that, we actually did very similar concepts with regard to just atoms and elements that we're going to scale it up to compounds. So the weight of a molecule, otherwise called molecular weight, the weight of a molecule, students usually do pretty good with this because you know the mass of the atom from the periodic table, so you just add them up. That's it. Okay? But there's kind of a subtle thing on these two slides, and I'll kind of draw it up here like this. Okay? We've been kind of talking in here where different compounds, CPD, there's different type of compounds. There's molecular, otherwise known as covalent compounds. And then there are ionic compounds. Now, if you get one repeating unit of a molecule, one repeating unit of a molecular compound, you have a molecule. Okay, if you get the weight of that, you have the molecular weight, MW, molecular weight. Okay. Now, compare that to this slide. So I don't mean to make a hairy deal out of this at all. Okay. A subtle difference, we said if you have a repeating unit of an ionic compound, you have an FU, you have a formula unit. So now we kind of run into kind of a little bit of semantics. If you want the mass of your formula unit, then you have a formula weight. So we have molecular weight and formula weight. How do you get them? You go to the periodic table, you add up the atoms that are in it. That's it. Okay?
Where are we in this thing?
9. On page 1 of 9. It's after 8.
So we skip 2 sections.
You're close. We can start all the way. It all looks like Greek upside down. Okay. So let's see how this works. It's easier to show you than to say what it is. And I get to this slide and I'm kind of like, I usually kind of pause and scratch my head, but technically a molecular weight is also a formula weight, but a formula weight is not necessarily a molecular weight. And I guess that goes to, we're going to talk about empirical formulas in part 10. I think that's what that is. All right, so let's do a problem. So you have a compound with nitrogen and hydrogen. Specifically, it's a molecular compound. Nitrogen's a nonmetal, and for identifying it as a molecular compound, hydrogen's a nonmetal. Okay. So the molecular weight, we're just going to go to the periodic table, take 2 nitrogens, add them together, periodic table, 4 hydrogens, and add them together, and add it all together and get how much it weighs. So let's not make it harder than it is. Now, you have to show all of your work. So on your test, if you have one of these, calculate the molecular weight or the formula weight. Show all of your work. So 2 times the decimal number for nitrogen, 2 times 14.01, and the units would be AMUs, plus 4 times 1.008 AMUs. Yeah, we kind of were clear at part 9. So, oh, yeah, keep going. Okay, and then we're adding, so we round according to decimals, actually multiplying, but the 2 and the 4 are exact. So we're basically adding, so we round to 2 decimals, so 32.05 AMUs is how much one molecule of N2H4 weighs. That's it. It's called the molecular weight, or MW, of hydrazine. Okay, we could do those. Those are kind of fun. Let's do another one. Let's do it for calcium nitrate. So since calcium's a metal, this is an ionic compound. So the weight of this is a formula weight. All right, so here we go. 1 times the mass of the decimal number for calcium, which is 40.08 AMUs, plus, now we have to consider our nitrate, but we have 2 NO3 groups. Okay, so we have 2 nitrogens, so 2 times the decimal number for nitrogen, 14.01 AMUs, plus 6, 2 times 3, 6 times the decimal number for hydrogen, or excuse me, for oxygen, which is 16.00 AMUs. Add them all up, actually multiply and then add. But again, the 1, 2, and 6 are exact, and so we're really kind of adding. So around, according to decimals, I get 164.10 AMUs. Now, if you put 164.1, then you like will lose a little point because it's 0.10. Pretty good. How much does it weigh in atomic mass units? The answer's up there. Yep. I'm just waiting, make sure everybody gets it written down. Okay. So these are due on Monday. Let me take a look. I don't know if I have these to show you. Sometimes I don't. 583. Yeah, I don't see this in my set of stuff. But I think it's not too bad. And then I say, is it a molecular weight or a formula weight? I don't have them to show you. Okay, so it's not time to go yet. So we're going to take it up a notch. Okay, molecular weight in AMU is how much a molecule weighs. Formula weight in AMU is how much a formula unit weighs. Well, I'm going to remind you the concept of a mole, which is 6.022 times 10 to the 23rd of anything. That's a mole. And the concept of molar mass, which is, we talked about elements, how much grams you have to set aside to get 1 mole of that stuff. Okay, so we're going to revisit that now, not with elements, but with compounds. So this little recall slide looks like, do you have this one? Yeah. Just to kind of remind you what a mole is. Okay, because now we're going to scale it from a mole of atoms to a mole of molecules, or a mole of formula units. Okay. So you're good with that. It's a counted number. There is uncertainty, 4 sig figs in Avogadro's number. So with any, this goes clear back to Unit 1. If you have an equivalency statement like that, you can make it into a conversion factor that you can use in factor label, have units cancel, be left with new units and that sort of thing. Okay, so we talked about with regard to atoms of any element. Okay, if you have 1 mole of atoms, then you have 6.022 times 10 to the 23rd atoms. If you have 6.022 times 10 to the 23rd atoms, you have 1 mole of atoms. Okay, just scaling it up then. If you have 1 mole of molecules, you have 6.022 times 10 to the 23rd molecules. And we can come up with kind of the same, pair of conversion factors. Okay, so you don't have to write anything down. And the next slide is similar, but instead of molecules, it's formula units. So if you have an ionic compound, again, it's a little bit semantics. So if you have an ionic compound, the repeating unit is a formula unit. So for ionic compounds, 1 mole of the repeating units, formula units, is equal to 6.022 times 10 to the 23rd of those. All right. So the other thing, this might look like deja vu, is the idea of molar mass. And In physical science, sometimes there are like the descriptive phrase that what a thing is, and it's very descriptive. And so molar mass is the mass per mole. And so for the elements, for instance, if we pick on carbon, we said it's a decimal number is 12.01. We said for carbon, that's its molar mass, 12.01 grams of carbon per 1 mole of carbon. Okay, very good. All right. So for atoms, for the elements, we said the molar mass is the decimal number, right? For carbon, it's 12.01 grams per mole. For oxygen, it's 16.00 grams per mole. For nitrogen, it's 14.01 grams per mole. So it's probably not too much of a leap now when we go from atoms to scale it up to compounds, so either molecule or a formula unit, okay? The molar mass of a compound is equal to its molecular weight or its formula weight. So like those problems we did just a minute ago, we came up AMUs of the N2H4, how much it weighs. Okay, we can take that same number, change it from AMUs to grams per 1 mole of the compound. It's the molar mass of the compound. So we're going to do some examples. Looks like you're all buying into this, because it's very true. So what we did with elements was we used the molar mass to convert from grams to moles, and we also used the molar mass to convert from moles to grams. And that's what we're going to do here with elements. And we're going to, this is kind of an aside, this is before we get to the conversion process. So if you're going to do a molar mass problem, a grams to moles or moles to grams problem with compounds, kind of on the front end, you need to show me coming up with the molar mass. So let's knock out the molar mass of C2H6 and the molar mass of NH4Cl. So this actually, you don't have to write it down if you don't want to. I'll put the word explicit means it's kind of over the top. Well, I shouldn't say over the top, because sometimes you need to be explicit. The next slide, if you don't write this down if you don't want to, because the next slide actually does more a simple way with the same problem. So if you have C2H6 and you want to come up with the molar mass, you could explicitly think of this way. Since I have 2 carbons and 6 hydrogens, it goes like this. 2 moles of carbon per 1 mole of the compound times the molar mass of carbon, 12.01 grams per 1 mole of carbon. And then we turn our attention to the hydrogen. There are 6 moles of hydrogen in the compound per mole of compound. The molar mass of hydrogen is decimal number for hydrogen, 1.008 grams per mole. So the molar mass of the compound is 30.07 grams per 1 mole. That's writing it explicitly. I would probably write it like this. This is how I would do my molar mass for C2H6. It looks very similar to my molecular weight calculation for the compound. Notice that actually kind of on the front end here, and I don't even have any units. I just simply take how many are in the molecule times the decimal number, how many of an element are in the molecule, times the decimal number for the element, plus how many hydrogens are in the element, times how much the decimal number for hydrogen. How many hydrogens, are in the compound. And then I add it all together, round to 2 decimals. Okay? So that's the abbreviated way, and that's how I would do it. But I want to remind you, sometimes we get in a hurry on our test or our homework, and we don't show this calculation of molar mass, but you need to. So I talked about kind of unpacking things. So if I unpack 30.07 grams per mole, what that really means is 30.07 grams of C2H6 per 1 mole of C2H6. That's what it really means. All right. So now let's knock out ammonium chloride, but let's do it the abbreviated way. So you take 1 times 14.01, because you have 1 nitrogen, plus 4 times 1.008, because you have 4 hydrogens, plus the chlorine then, 1 times 35.45, because you have 1 chlorine. And you add them all together, round to 2 decimals, and hopefully you get 35.49. And units would be grams per mole of this compound. So while I have this up here on the board, I'm going to kind of take from the molecular weight is in units of AMUs. You can get to, MM is our molar mass, right? And it's in units of grams per mole. From the formula weight, which is in units of AMUs, you can get to molar mass, which is grams per mole. Cool. So these felt very similar to the molecular weights and the formula weights. These are molar mass, grams per mole. So I think I may have mentioned this before, but when you're dealing with light elements, elements that are less than 10, you usually go with 3 decimals with regard to the decimal number from the periodic table. Okay, 3 decimal places. If it's heavier than 10, which I think it kind of cuts it out there, beryllium and boron, then you go with 2 decimals. And that works pretty well. Cool. So do you guys have this slide? Okay. You do? You don't? You do? Okay. Okay, so this actually, this can replace an assignment that you didn't do. So notice I have changed this from a regular assignment to an extra credit assignment.
Yeah.
So does that mean you're going to do it for extra points or you're not going to do it?
I need to.
Okay, yeah. So this would actually go into a pot that if you didn't hand in something, these points could go for that. Okay. So there, you grab a periodic table and you knock it out, right? It's kind of fun. You can do it in front of television. But don't forget to put your units. Okay. So let's go ahead and, like we did for elements, let's do some conversion problems with molar masses. Shall we? I think we shall. So hopefully you're going to kind of remember what we did with elements, because this is going to be similar. Now it's with compounds. So the thing in brackets, remember like I did before, the thing in brackets probably won't be there. Okay, thing in brackets is not necessary, so it might say how many moles is 1.28 grams of chloroform, and it gives the formula for chloroform. So we've diagrammed these before, so basically we are going, so how many moles? So I'm going to put an arrow over there, I'm going to go to moles, okay, is 1.28 grams, excuse me, CHCl3. So we're going from grams to moles. Well, if we have the molar mass of the compound, you can do that, and that's what we're going to do. We can accomplish that with the molar mass. So here we go. Kind of a step before you do your conversion is this one. So up there is calculating molar mass of CHCl3. So 1 times the decimal number for carbon, so 1 times 12.01 plus 1 times 1.008 for hydrogen plus 3 times 35.45 for chlorine. And then round to 2 decimals. And I get, that's pretty heavy, 119.37 grams per mole. 119.37 grams per mole. And I don't do it on my notes right here, but you might want to get in the habit of kind of unpacking that. The G/mole kind of bothers me sometimes. So what that means, like I said before, is 119.37 grams per 1 mole. And to me, if you do it this way, kind of unpack it, it's going to make more sense if you know if you have to flip it or just use it like that. So let's go ahead and work the problem. So our first term is going to be the 1.28 grams. Now, you don't have to put the CHCl3 if you don't want to, because we're only dealing with one species here. You can if you want to. But I usually put it over 1. Does this hopefully sound familiar? Feel familiar? So I want, in the next term, I want grams to cancel, and I want to be left with moles. So do we use the molar mass like kind of I did it, or do we flip it? How many people think we use it as it is? How many people think we flip it? Oh, there you go. We do flip it. So if we make our next term 1 mole over 119.37 grams, and again, you could put the CHCl3 if you want to, but it's not really necessary if you're only dealing with one thing. So doing it this way, then, of course, grams will cancel perfectly, and we're left with units of moles, and cheers to everyone. That's exactly where we wanted to be. So how many significant figures do we need to round it to?
3.
3. I agree. So this is what I got. So remember, significant figure-wise, the number I have down here, okay, this 0, although it's important, it's a placeholder. It's not significant. This 0 right here is significant because it's between 2 digits, bless you, that aren't 0. So this gives me 3 sig figs. Does that work? Yay. Okay. Well then. Let's do another one. In this one, what mass, so grams is going to go over there on the right. What mass, so grams, question mark grams, is 0.444, well, you know what I mean, moles of the compound. So again, if we have the molar mass of CH4, we can get there. So here we go. First step is going to be to knock out the molar mass. So if we take 1 times 12.01 plus 4 times 1.008 for the hydrogen, and then we round to 2 decimals, we get 16.04 grams per mole, which means for methane, 16.04 grams CH4 per 1 mole CH4. Cool. And we're going to use that as our second term to convert from moles to grams. So the first term is going to be that 0.4444 moles, or 0.4444 moles CH4 over 1. Now, how many people think we're going to use the molar mass just as it is, without flipping it? I see a head nodding. Yep. That would be the case. So if we go ahead and just insert our molar mass, 16.04 grams over 1 mole, the moles cancel. And we're left with units of grams, which is perfect. And how many sig figs? I'm liking 4. Yep. So this is what I got. 7.128 grams. 7.128 grams. Does that work? Yay! They're kind of fun. So those will be in the last section. Oops. So like my slides, it's a long story, but the one I edited is actually still at my desk, so I didn't edit this one. So I know that, yeah, let's go ahead, and how are we doing? No, let's just keep working. I know. I'm conflicted. Okay. Do you guys want to do that? Does everybody have calculators? Okay. Okay, yeah, let's do this. Let's take a minute and grab a calculator and go ahead and do these. These are similar to what we just did. One more problem. Actually, there should be some homework in here. I'm not sure. Okay.
Don't worry, it's coming.
It's coming. Okay. So, now this one, we actually took it up a notch and used Avogadro's number with atoms, and we're going to use Avogadro's now with molecules. Avogadro's number with molecules. Okay? So, how do you know you need to use Avogadro's number? Good question. Here where it says how many molecules, one of the things, like if I put question mark molecules over here, you know, they're pretty small. So there's a good chance that's going to be a big number. Okay? Notice the information given over here on the left is we're starting with 3.21 grams of the compound. So if I go from grams to moles, just kind of like one of the things I did before, and I can do that using the molar mass. Do you guys buy this? Now I can go from moles to molecules using Avogadro's number. Ah, yes. Using 1 mole is equal to 6.022 times 10 to the 23rd. In this case, molecules. All right, so let's do it. Here's what that looks like. So you saw the molar mass. The molar mass fits in it right early on. We're going to go from grams to moles. So the molar mass of C4H10 looks like this. We're going to take 4 times the decimal number for carbon, 4 times 12.01, plus 10 times 1.008. Kind of feeling familiar here. And we're going to round to 2 decimals, and we're going to get 58.12 grams per mole for the compound. And again, you can unpack that, so grams per mole. So here we go. What's our first term going to be?
Our given one, 3.21.
Yes, very good. Our given one. Perfect. We're going to put that over 1. Now, I'm not good at memorizing, do I divide or multiply? Sometimes you say, well, do I divide or multiply by the molar mass? I don't know. Set it up like this and just kind of let units cancel. So how many people think we're going to leave it not flipped? How many people think we're going to flip the molar mass? Me too. So flipping the molar mass, it looks like this. And again, you don't have to write the formula of the compound if you don't want to. You could just be the first term, 3.21 grams over 1. The second term, 1 mole over 58.12 grams. Now our grams cancel, we're left with moles. But we want to now go from moles to molecules. We're going to use Avogadro's number. So what does that next term look like? You want moles to cancel, we left with molecules.
0.0552.
Well, you went ahead and divided out, but I'm going to go ahead and put one more term here. So
6.02.
So you're right. Yep.
10 to the 23rd over 1 mole.
Yep, I agree. If we just, this is, yep. And it kind of wrapped around and ran out of room. So, yeah, if we just go ahead and insert the 6.022 times 10 to the 23rd molecules over 1 mole, now our moles cancel. It's wonderful. And the only unit we're left with is molecules. And we get to use scientific notation on our calculator. Yay! How many sig figs do we need to round this to? I'm liking 3 also. Okay, so what I got was this. No, I didn't. See? I know. Somebody do that for me. What'd you get? I need to fix my slide. 3.32. 3.32 times 10 to the 22nd molecules. What do you think? Is it 3.2 or 2.2? Thank you. See, it's okay. Just an extra step.
Yep. So that's what's next.
But it gets better. It's like,
This makes perfect here.
oh, wait a minute. I must have hit it. Ooh, spiders. I hate spiders. Oh my gosh. Hang on. Wrong computer. So, by my count, this is the 3rd time. I think this is like from last spring when I taught this class. I just did all sorts of extra credit. Oh, wait a minute. No, I didn't edit this. So these aren't extra credit. But we can make them extra credit. So what I did before is actually you have to do A and B, but C and D are optional. So let's begin. So this is 10 EC, 10 extra credit points, and this is 10 extra credit points. But you also have on your slide, which I'm glad, because they give the names, but they don't give the formulas. And I wanted to make sure that you knew the formula to work the problem. And I don't think I have these to pull up again. It's been that sort of morning. So if you have any questions, let me know, okay? I checked my email over the weekend, and that's a great place to stop.
Calculating things.
What's that?
Oh, it's going to be in the book. I was going to say, what are we calculating?
Yeah, it's in the book. Yeah, but the book just gives the names. I want you to have the formulas too.
Do we do these too? So we didn't get there.
No, we didn't get there yet. Okay? I don't think I have them. So unless you have any questions, that's it for today.
Pretty much the same thing.
you have homework to hand in yet, or?